Howdy, in this video we will finish up section 2.2, rules of inference. We'll cover things such as negation, conjunction, simplification, and the disjunctive syllogism. For the first part of section 2.2, we basically covered three things: modus ponens, double negation, and modus tollens. Now both modus ponens and modus tollens have an argument with the same exact major premise. It's the conditional, the hypothetical, if P then Q. So first premise, if P, then Q. First premise, if P, then Q. But in modus ponens, the second premise affirms the antecedent P, and then with those two premises, we're able to validly derive the conclusion Q. But for modus tollens, the second premise denies the consequent, so not Q, and then with those two premises, we're able to validly derive the conclusion, not P. In my mind, the most important thing to recognize is the distinction between sufficient and necessary conditions. When we consider the statement if P then Q, P, the antecedent, is sufficient for Q, the consequent. This allows us, insofar as we affirm that antecedent in another premise, to affirm that consequent. And also, when we consider if P then Q, the consequent Q is absolutely necessary for the antecedent P. And so, if Q is not the case, if the consequent is not the case, then necessarily it will follow that the antecedent is not the case. So P is sufficient for Q, Q is necessary for P. We also covered double negation. If we have the atomic sentence P, this is logically equivalent to the molecular sentence not P. We might think of it this way: if we have the statement not P, and then we deny that, the new denial, so to speak, cancels out the previous denial. And so we're just back at the statement P. So P and not P are logically equivalent. Or in other words, we can say that if we have the statement P, we could immediately infer the statement not P, and vice versa. If we have the statement not P, we can immediately infer the statement P. Let's move into the second part of section 2.2, and we'll continue a little bit more on double negation. So here's an argument, here's a proof. Let's step back and just consider proofs in general for a moment. So in any good proof, you number each and every sentence, 1, 2, 3, 4, 5, etc. You have the sentence stated, and then you must justify every single sentence. It may be, for example, just a premise, so it's justified as being a given premise. For example, sentences 1 and 2 are premises, and generally speaking, the other lines will be justified through some rule of inference, such as double negation. So sentence 3 is justified through double negation on line 2. Line 4 is justified through modus tollens with lines 1 and 3. Let's consider the argument. First premise, if A then not B. Second premise, B. And then eventually we're able to derive the conclusion, not A. But notice that on line 3, we double negated line 2 to get not B, because we want to deny this consequent, to thereby deny this antecedent. So the consequent right now is just not B. So to deny it, we have to have a negation there. We have to deny this, so we need the statement not B in order to do that. So this step here, or I should say this line 3, is really important in our argument to reach that conclusion, not A. We have to explicitly state that, hey, we are denying not B because we have the statement not B. Now you might wonder, couldn't we simplify things by just having the rules of modus tollens expanded, so to speak, so as not to require line 3? Couldn't we change the definition or modify the definition of modus tollens to account for the fact that the statement B is contradictive to not B, and have that be sufficient, that knowledge be sufficient to jump right to line 4? And that's what the Suppes and Hill textbook precisely does. Most textbooks don't, though. So here, for example, are two forms of modus tollens. We have this form, and we have this form. If we consider this form, we have the argument premise 1, if P then not Q, premise 2, Q, therefore not P by modus tollens. So that incorporated the notion of the fact that Q and not Q are contradictive vis-a-vis each other. So line 3 was not required. I suppose that's nice. Depends how you look at it. But most textbooks do not allow that. In fact, if you made this argument, I'm pretty sure most professors would mark you wrong. Most textbooks would mark you wrong. So most textbooks require an explicit line of double negation. You have to make this argument. And for the most part, I'll be sticking with the standard conventions, so I'll try to stick to this. There will be exceptions. For example, the next slide, I will be utilizing this shortcut. But in general, I'm going to stick to the standard conventions. I hope that makes sense. It's kind of interesting, though, that you can define modus tollens in slightly different ways. And there's no problem with that, as long as we have something that's valid. Part B of exercise 6 on page 60 of the textbook tells us that recognizing, for example, that x is equal to 0 is a negation of x is not equal to 0, avoid the rule of double negation in the following derivations. So here I will be using the, so to speak, more expansive definition of modus tollens. I'll be following the Suppes and Hill convention. Number 4, we want to prove that x is not equal to 0. We're given 4 premises. Sentence 4, we have x is equal to y. That's a absolute declarative sentence, and it appears in the antecedent to a conditional, so we can affirm that because of sentence 4. Hence, for sentence 5, we can say that x does equal z by modus ponens with sentences 1 and 4. Now that we have x equals z, we could affirm this antecedent to get that consequent. So for line 6, we'll say x is equal to 1 by modus ponens, lines 2 and 5. But notice that x equals 1 contradicts x is not equal 1, and through modus tollens we can get x is not equal 0. So for line 7, therefore x does not equal 0 by modus tollens with lines 3 and 6. For problem 6, we want to prove that x is equal to 0. We have a absolutely declared statement that's categorically the case. X is equal to y. And let's see. Well, x equals y appears here. We could affirm that and then get the consequent. So sentence 5, we can get y is equal to w by modus ponens with lines 2 and 4. So now we have y is equal to w. That is the case. That appears in the antecedent to a conditional. So now we can get y does not equal 1 by modus ponens. So line 6, y does not equal 1 by modus ponens, lines 3 and 5. And we have y doesn't equal 1, but that contradicts y is equal to 1. So we can deny that consequent to deny that antecedent. And if we're denying the antecedent, x is not equal 0. It must be that x does equal 0. So line 7, x equals 0 by modus tollens with lines 1 and 6. All right, here are 2 additional rules of inference. We have the rule of adjunction and the rule of simplification. Adjunction is also called, so aka the rule of conjunction. Most contemporary textbooks will call this the rule of conjunction, or CONJ for short. So with the rule of junction, or also known as the rule of conjunction, we can combine 2 true sentences together via the and sentential connective. For example, first premise, a square is a rectangle. Second premise, a square has 4 right angles. Conclusion, therefore, a square is a rectangle and a square has 4 right angles. First premise we might label as R. Second premise, let's label as A. And then our conclusion is therefore R and A by the conjunction rule with lines 1 and 2. We can also abbreviate this as A if we refer to it as the rule of adjunction. Then we have the rule of simplification. Thankfully, all textbooks that I'm aware of use the same name, which is nice. Here we can separate two true sentences. We have a conjunction, say A and B, and then we can simplify it to get A. For example, premise: real analysis is a branch of math, and abstract algebra is a branch of math. Conclusion: therefore, real analysis is a branch of math. First premise, we might say this is R and A. Conclusion: therefore, R. With the Suppes and Hill textbook, we can also conclude, therefore, abstract algebra is a branch of math. So therefore, A. And this is just by the simplification of sentence 1, simplification, sentence 1. However, note that in some textbooks, in many textbooks, in fact, you could only simplify the first sentence of the conjunction. So you couldn't simplify and get abstract algebra as a branch of mathematics. What you would have to do is use the so-called commutative rule and flip these two sentences, so from R and A to A and R by the commutative rule, and then you can get A by itself through simplification. And we can abbreviate simplification by S or by SIMP. Depends on the textbook. Together, let's do some proofs. This is part B of exercise 7 on page 63. So number 4, we want to prove the conjunction B and D given our two premises. We do have a B in the first premise is in a conjunction, and then we have a D in a conditional as the consequent. So we're going to want to get B out of that conjunction, and because B is the case, we could affirm the antecedent there to get that D as the consequent. So for line 3, the first move is just to get B by the simplification of line 1. And then for line 4, because we have B is the case, we could affirm the antecedent to get the consequent D by modus ponens with sentences 2 and 3. We want the conclusion to be B and D. Sentence 3 has B, sentence 4 has D, so for 5, therefore B and D by the conjunction of 3 and 4. For 5, we want to prove not S and Q. So let's see what we have here. We have two conditionals, and we also have a negation of a conjunction. But notice that this negation is applied to T and R, and T and R appears as the consequent of a conditional. So we do have modus tollens for line 4, because we could deny that consequent, we could deny the antecedent, so we get not S by modus tollens with sentences 2 and 3. And then, because we have not S, we could affirm that antecedent in a conditional to get Q, the consequent. So for line 5, we can get Q by modus ponens with lines 1 and 4. And now we have not S, line 4, we have Q, line 5, and then we can just combine them. So for line 6, therefore, not S and Q by the conjunction of 4 and 5. Or alternatively, we can say this is an adjunction of 4 and 5. For 6, we want to prove the conjunction A and C. Okay, so we have a conjunction and a conditional there. We have a B here that's negated, and we have a B there. So we're going to want to get that B out of that conjunction. For line 3, depends on the textbook. Sometimes you would actually have to do the commutative rule first. You would have to say not B and A by the commutative rule with line 1. And then you can simplify for line 4. We can get not B by the simplification of line 3. And we have not B, that's denying the consequent there, so we can thereby deny the antecedent. So for line 5, we can get not C, modus tollens, lines 2 and 4. Not C is just C. For 6, we can get C by the double negation rule on 5. And then for 7, we can get, let's see, an A by the simplification of line 1. And then for 8, we can get A and C by the conjunction rule with lines 7 and 6. What I did a little bit different than the textbook is to apply the commutative rule. The commutative rule just allows us to go from, let's say, P and Q to Q and P. Because in a lot of textbooks, you can only simplify the first sentence of a conjunction. The Suppes and Hill textbook has not mentioned the commutative law yet, but I have nevertheless resorted to it, so I better place a brief note about it here. And we can just use our common sense here. So if we have the statement P and Q, that's logically equivalent to the statement Q and P. The order simply is not important. And likewise with a disjunction, P or Q, that's logically equivalent to Q or P. And with many textbooks, if you have a situation like A and B, it's a conjunction and you want to simplify and you want B by itself, it turns out that they have developed the law of simplification such that you can only simplify the first statement. So if you want to simplify to get B by itself, you have to resort to the commutative law first. So you would have to say B and A by the commutative law, and then you can get B by simplification. So that's important to note. Many textbooks are that fussy. Let's take a look at disjunctions once again. And remember, in a disjunction, the sentential connective is the or. For example, the disjunction X or Y. However, the word or can have two meanings, so therefore there's an ambiguity to the word or. And this is entirely intolerable in mathematical logic. We need a precise meaning. On the one hand, the or can be exclusive. And indeed, in everyday language, in ordinary conversation, we often use the or in an exclusive sense. For example, today is Monday, or today is not Monday. One must be true and the other false. Both cannot be true. It either is Monday or it isn't, and that's that. But on the other hand, the or can be inclusive. For example, today is Monday, or it is hot outside. At least one of the choices must be true. However, both can be true. It can be Monday, and it can be hot outside. And this is very important. By default, mathematical logic takes the inclusive meaning. Always, always, always. It's always the default in how we interpret the or. For example, let's say we have the following argument. So 1, we have the premise X or Y. 2, we have the premise X. And let's say we concluded that therefore Y is not the case. Does this argument work? Well, certainly not, okay? Because the or is inclusive. Just because X is the case, it does not mean that Y is not the case. Indeed, X and Y can both be the case, so this is totally invalid. But this raises an interesting issue that is important, it seems to me. And it seems like the textbook doesn't even address this. It should, but at any rate, let's say we're confronting a situation where the or must be exclusive. Indeed, in everyday language, like I said, we often use the or in an exclusive manner. So let's say we're confronting a situation where A is the case or B is the case, but not both. So we have A or B in an exclusive manner. How would we translate that into mathematical logic? We want a useful sentence that actually represents what we want. And we certainly can't just say A or B and leave it at that, okay? Because the or is inclusive, but we want exclusivity. Now we can do this. We just have to think about what we are expressing. So far we have A is the case. So right here, that is, we have either A is the case or B is the case or both are the case. So we want to deny that both are the case. So therefore, we should say and, not A and B. So you see what I did there? With this addition, I have A and B together, A is the case and B is the case, but I'm denying that. So I'm saying A and B are not the case. And we have here this and connective to form this molecular sentence. So now we have, starting here, A is the case or B is the case or both are the case. But this addition is negating that A and B together are the case. So therefore, we have translated correctly A or B exclusive into the language of mathematical logic. So I think that is very handy to think about and to keep in mind if we're dealing with a situation where we have an exclusive OR and we want to translate it into mathematical logic. We have to keep in mind that the OR is inclusive. So we're going to have to, so to speak, make some modifications, or we're going to have to really just add some additional constraints. And that's what I did. Here, this is an additional constraint, and not A and B. Modus tollens ponens is another rule of inference. Most textbooks simply call this the disjunctive syllogism. Now, if it was up to me, I don't know about you, I would have all textbooks call this modus tollens ponens, because isn't the Latin cooler? Well, I certainly think so. But in any case, the modus tollens ponens rule of inference is really the only valid form of a disjunctive syllogism because the OR is an inclusive OR. By denying tollendo one side of the disjunction, we affirm ponens the other side. So here's the argument. Premise 1, a disjunction, P or Q. Premise 2, a negation, not P. And then we have our conclusion, therefore Q. Now note that the disjunction, P or Q, is true insofar as at least one of those options, P or Q, is true. So if we know for a fact that P is not the case, it must be the case that Q is the case. And the textbook will abbreviate this as TP for tollens ponens, but because most textbooks call this the disjunctive syllogism, we can just say this is DS for short. Here's an example from the textbook, page 65. Either the substance includes hydrogen or it includes oxygen. Second premise, this substance does not include hydrogen. Conclusion, therefore the substance does include oxygen. Very briefly, I want to look at part A of exercise 8, just to make sure we understand what's going on with these three examples. So number 1, that man is either a lawyer or he's a politician, but he is not a lawyer. Well, therefore, he's obviously a politician. That's a disjunctive syllogism, also known as modus tollens ponens. I don't know what's worse, by the way, being a lawyer or being a politician. What's worse? I think I can only conclude logically that being a politician is probably worse. Sentence 2, the port of New Orleans is either on the Gulf of Mexico or is on the Atlantic Ocean. It is certainly not on the Atlantic Ocean, so therefore it is on the Gulf of Mexico. Sentence 3, either the internal energy of an atom can be changed continuously or it changes only in steps. The internal energy of an atom cannot be changed continuously, therefore it changes only in steps. Before concluding this video, let's do 3 more proofs. This is on page 68 of the Suppes textbook. Number 5, we want to prove H. We're given the premise not S. We're given the disjunction S or parentheses H or G, close parentheses, and the premise not G. What can we do? Well, we do know that not S, so in this disjunction, we can say it must be the case that H or G. So let's do that. For line 4, we can get H or G by the disjunctive syllogism with lines 1 and 2. Alternatively, we can use the Suppes and Hill notation. This is just TP 1, 2 for modus tollens ponens. Line 3 says G is not the case, so we have this disjunction here. We can get H, but to be really, really careful, because some textbooks require this, for line 5, we'll first resort to the commutative rule to get G or H. So that's just the commutative rule or commutative law, line 4. So that's a little bit different than the Suppes and Hill textbook, but that's okay. So we can deny this G, because we know G is not the case, hence for line 6 it therefore follows H by the disjunctive syllogism, lines 3 and 5. So let's move on to number 6. We want to prove P. We're given 3 premises. We have a conditional, we have something that's double negated, and we have another thing that's negated. Well, we do have this not T. We know by the double negation rule that's equivalent to T, and so with this conditional we could affirm the antecedent to get the consequent. So the first step for line 4 is just to get T by the double negation of line 2. Not T is equivalent to T by double negation. And now for line 5 we can get that P or Q because we could affirm that antecedent to get that consequent. So we have P or Q by modus ponens, lines 1 and 4. We have this not Q, we have this disjunction, so eventually we can get that P. For line 6, let's just be very careful here and just say Q or P by the commutative rule, line 5. And then for 7, because Q is not the case, P is, so therefore P by our disjunctive syllogism. This is with lines 3 and 6. And for number 7, we want to prove R. So what can we do here? We have this not S as a premise. We have this disjunction, not Q or S. So we can get a not Q from that. For line 4, to be extra careful, let's just say this is S or not Q by the commutative rule. Line 1, we have not S from line 2, so for 5 we can get not Q by our disjunctive syllogism, lines 2 and 4. Notice that we have a Q in the consequent of a conditional. We have this not Q, so we can deny that consequent to deny the antecedent. So we can deny this. So for line 6, we can get not parentheses R and S by modus tollens with lines 3 and 5. We have these 2 negations, but by the double negation rule we can get R and S. So for 7, we can get R and S, double negation. Line 6, we want R as our conclusion, but we have the simplification rule. So for 8, therefore, it does follow R by the simplification of 7. My plans, at least presently, is to do a bonus video as a brief recap or summary of section 2.2 and then to move on to section 2.3.